topic is Hamilton's variational principle. So before starting this topic, let's discuss about the configuration space. Okay, because the Lagrangian mechanics is valid for the configuration space. Okay, what is the configuration space? See, a problem involving n particles can be treated as one of a single particle moving along the 3n dimensional space. Means, see, generally we consider 3-dimensional space and n particles are moving. So instead of n particle, we consider a single particle, but we increase the dimension. Okay, so instead of using n particles in 3 dimensions, we use one particle in a 3n dimensional space, and this space is referred as a configuration space. Okay, so it simplifies our problem. Okay, and a single particle is system point. So motion of a system point in configuration space is called the motion of the system between any two given instant. Okay, so this configuration space has no necessary connection with the real 3-dimensional space. Okay, and what is the Hamilton variational principle? Hamilton principle for the conservative system is state that the motion of a system in a configuration space from time t1 to time t2 is such that the integral s, or sometimes is represented as I, is an extremum for the path of the motion. Okay, it always remains extremum. So that is the Hamilton's variational principle. Okay, so what is L? L is nothing but T minus V. And that is the basic definition. Okay, let me write down. The motion of the system from time t1 to time t2 is such that the integral this is an extremum. Extremum means it can be maximum or minimum for the path of the motion. Okay, so how we can derive this result? See, let us consider a conservative system of particles, and we are employing the generalized coordinate. So integral can be written as this: t1 to t2, kinetic energy qj dot minus potential energy. For a conservative system, potential energy is only a function of the coordinate, generalized coordinates. Okay, therefore according to the Hamilton principle, this. Okay, or we can write down it as T2. This variation can be written as sigma j delta t over delta qj del qj plus delta t delta qj dot del qj dot minus del v del qj dt is equal to 0, or j delta t upon delta qj minus delta v upon delta qj dt plus t1 to t2 j delta t delta qj dot del qj dot dt is equal to 0, or t1 to t2 sigma delta t delta qj minus delta v delta qj del qj dt plus t1 to t2 delta t delta qj dot and d by dt delta qj dt is equal to 0. Okay, and integration by parts, this second term, this, see, the first term remains as it is, but second terms will be some interesting part. See, we can write down it is in this form. Suppose suppose d by dt, suppose this term first into second. So what is the differentiation? There are two parts. So the first term into differentiation of second, which is nothing but this term, plus differentiation of first term into second term as it is. So this term I can write down this minus this. Okay, it is very interesting. So I am rewriting this equation. So I am writing it again, and this is replaced by this minus this. Okay, so the first part is as it is, sigma plus integration, this whole differentiation del t dt, same, the sigma as it is, t1 to t2 minus t1 to t2 sigma dt is equal to 0. Okay, so in such a variation there is no coordinate variation at end point, so the variation of delta qj at end points is 0. So it means this term goes to 0. Okay, the total, because it's a total variation, so it will be 0, and just write down it again. So this part and this part I am writing it again, t1 t2 dt minus this is 0. Okay, or combine both the equations together. So minus d by dt okay, since each delta qj are independent of each other, the coefficient of every delta qj should be equal to 0. So it should be 0. So thus equating the coefficient of jth coordinate to 0, we get this equation: delta t delta qj minus delta v delta qj minus del by del t delta t by delta qj dot. See, because potential is not dependent upon qj dot, so I can write down del v by del qj dot because it is 0. Okay, so what is this now? T minus v, and similarly t minus v 0. So del L by del qj minus d by dt del L by del qj dot is equal to 0. Okay, where L is the Lagrangian. So what is this? So Lagrangian is a for conservative system t minus v, and this equation is nothing but known as the Lagrangian equation of motion. Okay, so from the Hamilton variational principle we achieve the equation of motion. Okay, that was our basic aim. It is a second order differential equation in terms of the time as an independent variable. Okay.